Okay, shall we start? Yeah.
Yes, sir.
Yes,
Oh, okay. Good evening, everyone. Thanks for joining in. And agenda for today's session is to carry out revision for week 3 and week 4 of ATB towards preparation for quiz 1. So how we will proceed? We will first revise the important concepts which were covered in week 3 and week 4. Thereafter, we will see the PAs and GAs of those weeks, and then we will proceed to the previous year question paper pertaining to these weeks. And at last, what we will do, we will take on all the questions. If somebody has got query about other weeks also, so we can consider this session as a final session for the revision for quiz 1 for ATB. Okay, so with that context, I will just share my week 3 notes and we will cover the concepts of week 3. I hope my screen is visible to all of you and it is clear.
Yes, sir.
Okay.
Yes, sir.
Okay, so in the week 3, the main concept which was covered, it was like that how do we create the genome from the pieces, or we call that as a read. So we have got many reads which are there. So how to make the full genome from that? So computationally, it is not easy to read the entire genome if the genome is available also. So they give an example of the newspaper, that if you shred a newspaper and then you want to rebuild it, how difficult it is. You have to stitch all the pieces of the newspaper. So in the similar fashion, what do we do? That we have got a genome. So we have got the multiple genome copies. And from that, we can generate the reads. So reads are the small pieces. Now, these small pieces which are there, now from that, now we build the genome. So that is the main part. Okay, so it is genome sequencing. Okay, so there are 3 ways how to do that. First, we have to, if we have got a gene, for example, on the left side where my cursor is there, you can see the gene. So we make a k-mer composition. So k-mer composition, I will share the formula for that. It has come in one of the PYQs. So if you have got a, for example, I'm just giving an example, ATG, ATG, CGT, ATG. And I have to make a k-mer of length 3. Okay, so this will call as K, and N is the length of genome. So the formula that how many k-mers I will have will be N minus K plus 1. Okay, please remember this formula. So we can see, for example, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So N is 12. And k-mer, we need length of 3, for example. So we can see here that we will have ATG, TGA, GAT, again ATG, TGC, GCG, CGT, GTA, TAT, and ATG. And if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this will be 12 minus 3 plus 1 is equal to 10. So exactly we get 10 k-mers. We can have 4 k-mers also. Okay, in that case, we will take ATGA, then TGAT, GAT, G, then ATGC. So this how we make the k-mers. So first part is to make the k-mers. And from that k-mer, we can make the graphs. So the first part, what professor covered, that if we have got the k-mers, for example, this is, I will take a small example. So A, T, G, C, T, A, G, T, for example. So what do? We make the first k-mers, and from that we build graph. So from here, if we make 3 k-mers, composition 3 length k-mers, so we will have ATG, TGC, GCT, CTA, TAG, and AGT. And now we break this. So these are the reads here. Now we break them into pairs. So this will become AT, TG, TG, GC, GC, CT, CT, TA, TA, AG, and AG and GT. Now, when you build the graph from this, so for example, we will not be given this gene. We are given only the k-mers, for example, in a question. So we have to build the graph. So how to build the graph? There are some clues how to do that. So from this, first we try to find what is the start point, and we also try to find what is the end point. So this, if we can identify these 2 points, then our life becomes easier. So how to find the start point? So start point will be a prefix which is not their suffix in any pair. Okay, so I'm just considering this sx minus anywhere. So we can check from here, that check from 80, for example. 80, is it there anywhere in the suffix? So it is not there. So easily we can find here that 80 is the start point. If we check others, so TG is there in the suffix, so it cannot be the start point. GC is there, GC. CT is there, CT. TA, TA. AG, AG. So it cannot be the start point. So only we have identified now 80. Now we come to find the end point. End point is opposite. It will be the suffix which is not prefixed in any pair. Okay, so now we check the suffix from here. So TG is there in the prefix, GC it is there, CT is there, TA is there, AG is there. Only GT is the one which is not there in any prefix. So we have find out now the endpoint also. So we know GT. So we know, if now we will start building the graph. So we know there is an 80 and we know there is a GT here in the last. So this is a very simple graph because we have built from a normal gene, but in the coming time, when we will be solving the GAs and the PYQs, we will see some complex problem. So we go from 80 to TG. From TG, we go to GC. GC to we go to CT. CT to we go to TA. TA we go to AG. And AG we go to GT. Now, if we are given this, now we have found the path. And how to build the path from here? So see, here TT is common, so this will become ATG. Now here TGGC, so G is common, so TGC will come from here. GCT, here T will come, from here A will come, here G will come, and T will come. So this how we build the sequence. So this is one example, how do we do that? And this is the graph, which we call the terminology I will cover in the. So this is the basic working concept, how to find. So here I have covered the formula n minus k plus 1. And Hamilton path is a path where a path is visiting every node in the graph exactly once. So that is the Hamilton path. You are given nodes and we have to find a path. So a Hamilton path will be the path where every node is visited only once. And there is another called like a Eulerian path. So Eulerian path is the path in which every edge is visited every time. So Hamilton is node and Eulerian is every edge. Now, how to find in a graph that it is a Eulerian path or it is a Hamilton path? So basic clue the professor had covered, that in any path, if we have got some nodes, 1, 2, 3, 4, 5, 6. So if they have even number of outgoing and incoming, then this will be having a path. If any node is having, for example, odd number, okay, so here you see it is having incoming 1, 2, and outgoing 1. So if you make this, so this graph will not have a solution. Here we cannot find. But if we remove this and if we make it even number, then it will have a path.
Sir, can you explain this once again?
Okay, so
Sir, and is this rule valid for Hamiltonian path or Eulerian path?
For both, okay, for Eulerian also and for Hamilton also.
Okay.
Okay, so you take an example that you have got this node, you have got this node, and you have got, for example, this node also, and finally here you are making a. So I am taking a small example. So can we find a Hamiltonian path that starts from here, from 1, it visits all the nodes and comes back to 1? Can we find that? So we start from, for example, so here we check, this is the node 1, which has got outgoing 2, incoming 1. So if we start from here, it is 1 to 2, then either it comes to 1, and as soon as it comes to 1, it is visiting this 1 twice, so it is not a Hamiltonian path. So what we can do, we can go from 1 to 2 to 3 and it stops here. So this is also not a Hamiltonian path because all the nodes, they have not been visited. Is that okay?
Yes.
And see, yeah. And if you see 3 also has got incoming 2 and outgoing 0. Okay, so this is also in contravention to that every node should have even number of outgoing and even number of incoming routes. Then it can have Hamiltonian. Okay, and you can go through the example. Professor has covered 2 more examples in the lecture. So it is just to see the graph and to find visually that whether it has got a solution or not. Is that okay? Can we go ahead?
Yes.
Okay, so this is the Euler theorem, okay, which I had covered, that if all the nodes have even number of incoming and outgoing nodes, it will have a Euler's path. Okay, and how to solve the Euler's path? That we do it recursively. So we start from any node and we come back to that node. So when we come back to that node, now we see which all other nodes have not been visited. So now we will start from that node which has not been visited, and now we make a round and come back to that node. Now again we see which all subpaths they have not been visited. So again we go to that, and now we add all this to get the path. Okay, and the example has been given in the lecture. So this is how do we do it. Shall I show one example for this?
Yes, sir.
Okay, so I will open the 3 notes. We will take one example from here, that how do we do that. So here I hope. So we will take this example, we will solve this using this concept. This is visible to all of you?
Yes, sir.
Okay.
Yes, sir.
So now if we do it, without any that Euler's theorem, then it is very difficult to find a path. Now what do? We pick up any node. For example, we pick up a node, for example, 0, 0, 1. First of all, we check that all the nodes have got even number and outgoing and incoming. So see here, it is 2 outgoing, 2 incoming, 2 incoming, 2 outgoing. Here, 2 outgoing, 1 incoming, another incoming, 2 outgoing. Here, 2 outgoing, 2 incoming, 2 incoming, 2 outgoing, 2 incoming, and 2 outgoing. So all the nodes are fulfilling the criteria of the Euler theorem. So it means that there is a path. Now, how to find that path? So we take, for example, 0, 0, 1. We start from here. We take anywhere. We go to outgoing. So we come to 0, 1, 1. From 0, 1, 1, we take, for example, here. We come here. We come to 1, 1, 0. 1, 1, 0, 2, we go to 1, 0, 1. 1, 0, 1, we go to 0, 1, 0. We come here 0, 1, 0, 0. And now finally we come back to this node. Okay, so we have made this route 0, 0, 1, 2, 0, 1, 1, then to 1, 1, 0, 1, then 1, 0, 1, to 0, 1, 0, 1, 0, 0, and to 0, 0, 1. So this one path we have found. Now we have to see which other path we have not been able to go. So we can find that this is one path which we have not gone. This is one path. Is that okay?
Yeah.
Okay. So now what we will do, we will start now from 1, 0, 0. We go to 0, 0, 0, make a round trip around 0, 0, 0, go to 0, 0, 1, come back to 0, 1, 0, and now come back to 1, 0, 0. So we have found that we have covered this part. So we can write this 1, 0, 0 to 0, 0, 0 to 0, 0, 0 to 0, 0, 1 to 0, 1, 0 to 1, 0, 0. This we can write.
Yes.
Okay. Now we see the third here, which has been left now. So this has been covered. This has not been covered. This one. And this has not been covered. This one. So we can start from this node. So we come to 1, 1, 1. We make a round of 1, 1, 1. We come to 1, 1, 0. We go, come back, and from here we come back to 0, 0, 1. So this third path, okay, we have got 0, 1, 1 to 1, 1, 1, 1, 1, 0, 1, 0, 1 to 0, 1, 0 to 1, 0, 1, and to back to 0, 1, 1. Now all the nodes we have visited, all the edges have been visited, or something has been left. Okay. So
One edge is
One edge is left.
yeah, so this edge is left. This one. This one is left.
Yeah.
No, from 0, 1, 1 to 1, 1, 0, that edge we covered, but this one is not covered. 1, 1, 0 to 1, 0, 0.
Okay, this one.
Yes, yes.
11001.
Okay, okay, okay. So first, okay, let's cover this 0, 1, 1 to 1, 1, 0, 1, 1, 0, 0. And from there we can go to 0, 0, 1, and from there we can go to 0, 1, 1. So we have covered this outer. Is that okay? And
Yes.
to cover this now 0, 1, 1, we have to cover this edge. This is the edge, na?
Yes.
Okay, so we start from 1, 1, 1. We come to 1, 1, 0. We go to 1, 0, 1. We go to 0, 1, 1. And then finally we come to 1, 1, 1. So this is the fourth path.
Yeah.
Okay.
Fifth.
And now you just stitch these paths wherever, for example, this 0, 0, 1, it went to 0, 1, 1. So we have got another one path which is starting from 0, 1, 1. Okay. So that path which is there from the 0, 1, 1, you stitch it here. Is that okay?
Sir, can you once again?
Yeah.
Okay. Just hold on. So this is, can I take a small example? This is a very big example.
Yes.
Yeah,
yes.
yeah.
Yeah. Okay. So small example was here. Okay, we'll be solving one PYQ question. In fact, there are two questions on the same concept. Can we do it that time?
Yeah, okay.
If you allow me. Okay, okay, we'll be solving. We have got
Yes.
that. Okay. Yeah, okay. So we have to understand this again, two parts again, which are the main parts, that nodes have to have even number of incoming and outgoing nodes. Then it has got a Euler's path, definitely a Euler path.
Okay.
Okay.
Hmm.
Every Eulerian graph is balanced, and every balanced graph is Eulerian. Balanced means that even number of that. But the problem with the Eulerian path is that you can find more than one genome sequence also, because you can go from here, and you can come here, and you can take the north route or you can take the south route. So there can be two genome sequences. So that is a problem when we do the single pair read Eulerian path problem. So to solve that, we have got a pair of distances. So what do? We make the pairs. I'll just take this example. So here we have got two things. We have got one is the k-mer length. For example, I call it as D or K. And for example, in this case, we take it as 3. And another is distance, which is D. And we, for example, in this case, we take 1. And how to make those k-mer pairs? That we take, for example, TAA. This is D1, so we leave this and we take the next pairs, GCC. So this is one pair, GCC. Second, now we slide the window. Now it is AAT. This is the distance and it is CCA. Now we slide the window. It is ATG and this will become CAT. From there, TGC, and now it will be ATG. So before solving this, I will cover first in the Eulerian how we build the graph here. Okay, is that okay? And in the similar fashion, we build this graph. So from here only, we take an example from week 3 only. So we will build a Hamilton path or this graph which they are asking that how to build the graph. Okay, so in the real world, we don't get the genome. We will be given these pairs only. Okay, and we are asked that find out which are the genomes which are possible from here. Okay, so how to go about it? So same steps are there. We AAT, we break it down to AA, AT, ATG, we break it down to AT, TG, ATG again, it is twice, so we write it twice. It is thrice, ATG, AT, TG, then CAT, CAAT, CCA, CCCA, GAT, GAAT, GCC, GCCC, GGA, GGGA, GGG, so it is GGGG, GTT, GTTT, TA, TA, double A, TGC, TGGC, TGG, TGGG, TGT, TGGT. So what do we do? First of all, we find the start point. We try to find the start point. So start point, we start looking in the prefixes which should not be there in the suffix. So this is double A, and if we see here, the double A is here. It is there. Double A is here. So it cannot be a single point. 80, it is there. 80 is there. CA is there. CC, if we see CC, yes, it is there. GA, it is there. GC is there. GG is there. GG is there. GT, we find. So GT is also there. We find TA. So we find this TA which is there. TA is not there anywhere. So we have found that one of the starting point can be TA. Okay, then we check others. TG, TG, TG. So T is here. So we have got only one start point in this. Now we find the end point. So end point we do for the suffix. So check for 80, it is there. TG is there. 80 we have checked. CA, 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 CA is there. AT is there. CC, CC is there.
TT is not there.
TT is not there. Okay, so one by one we can check, and we can check others also, because in some questions, just to confuse us, they can give us 2 starting points and 2 endpoints also. Okay, just to check whether the path is possible or not. So now with this background, we know in this graph there is only one start point and one end point. Okay, so we can mark this TA here and TT is here. Okay, now we start with TA. So where is TA? Is here. So TA will go to AA.
Sir, what in case if there are 2 endpoints and start points? Then what? How will you approach the problem?
Okay, so if there are 2 start points, they can ask you one question that there can be this subpath. So in that you see that subpath, which is possible or not, number one. Number two, if they ask you that there is a path which can cover all the nodes, then answer is no. Okay.
Okay.
Okay. Okay, so now we start building the path now. So we go to TAA. So we strike this, we have marked this, TAA. Now we go to AA. Where is AA? AA is here. So from here we go to 80. So we strike this. Now from AA, we can go only to 80. But 80, you see, there are ATG, ATG, ATG. Okay, other 80 is there. So from ATG, what we have to do, make to TG, it can take 3 routes. Is that okay? And we strike this also, that we have covered this also.
Yeah.
Okay. Now we come to TG. Now see, TG also, it can go to GC, GG, GT. Okay.
Yeah.
Okay. So we make one GT here. We take TG one route here. For example, GC. We take one route here, which is GG. Okay. So we have covered this path also. 3. Now we come to, for example, here GT. Okay. From GT, it goes to only TT, which is my endpoint. Okay. So now this cannot be explored further. Now I come to, so I have covered this also. I come to GC. So where is GC? GC is here. It goes to CC. So GC goes to CC. Now where the CC goes? CC goes to CCA. So it goes to CA. Where is CA goes? CA goes to 80. So this CA will come here, 80. So this I have covered. Now I check GG. So GG has got GGG. It means it has got a part 2 itself. So I stack this. Now I got GGA. So it goes to GA. I stack this. Now from GA it goes to GAT. Okay. So now the path is ready. Just give me 30 seconds. I am getting one office call. I'll just come back. Okay, so this path making is clear to all of you, how we build this path? This graph, okay, sorry.
Yes,
Yes.
clear.
Okay. Okay. So now, how to, when we said that okay, in this kind of problem, there can be 2, 3 more paths. Okay. So we see how we build the path now. So we start from TAAA. So it will give me TA. Come to AT, TAT. I come to TG. So it give me TG. I take the north route. So I come to TGC. CC, again C. I come to CA. I come to AT. From AT, I come again to TG. So I get TG. Now, from TG, I can come to GG. So again, I get TG, GG. And GG is making a route. So again, one more G. Here, GA. From GA, I go again to T. And it has got 3 paths. So 2 we have covered. We have got another path. So ATG. And from here, I come to this was GTT. So this was GT and TT. So this is how we can build the path. But this path, what we did, we went to north and then came to south. Now, if we do opposite, for example, we come to south, TAA, TG, and from here come to south. So we'll get GGG, A, T, G, C, C, A, T, G, T, T. So this is a separate path. So this is a problem. We can get 2 sequence paths if we are using a single read and single pair only. Is that okay? Clear? This one? This part?
Yes.
Okay. And that's why what do? We use now the distance and double pair one. So how we will solve the same question using the double pair, and how we will get a different answer. So for example, if we consider that the sequence, for example, actual sequence is this one. This is the sequence. So from here, what we will do, we will build a 3-kamer, and with distance t is equal to 1. So what it will give me? So it will give me one TAT CCA, TAT CCA, which can be broken down to TAAT CCCA. So this is my first. Second, it will give me ATG CAT. This I can break down to AT TG CA to AT. Now it will give me TGC. So can I make it like a small sequence? So to make things slightly easy, otherwise it will become very long. TGC, and this will become ATG. So TG, GC, AT, TG. Because we had faced the problem here, north and south. So we can, if we cover till this point only, so we'll get the same concept clear. Because after that it was same. Is that okay?
Yeah.
Okay. So now we have come to TGC. So we come to GCC, and after ATG is TGG. So this will become GC, CC, TG, GG. And here we build the others. So here after GCC is CCA, and after T, this was TGG, GCC, TGG. This will become GGG, CCCA, GGGG. We come to now from GCC to CCA. And here we come GGA, CCCA, GGGA. Now we come to CAT. And here we come GAT. So this CA, AT, GA, AT. And here, so let's cover here the full CAT. Now we come to ATG, and this will be ATG, ATG. So ATTG, ATTG. That's ATG. So we have come now here TGG and ATG, TGT, TG, GG, TG, GT. And this will be the last one, GGG, and this will be GTT. So GG, GG, GT, TT. Okay, so we have got all this. Now using the same philosophy, how we used to find the start point and the end point. So now I start checking the prefixes okay, like two prefixes okay, or the TA, for example. So we see is TA is there okay. So TA is not there anywhere. So I know my start okay, is TA. So when I say TA, it will start with TACC. Okay. And now I check for the suffix. AT is there, TG is there, GC is there, CA is somewhere, CA is there, CA was TGG.
It's there, yeah. C is there.
Oh, yes, here, it is there. Okay, so it is there. AT is 80, 80 is there, yes. TG is there, GG is there. Only TT is not there. So this is my, so from here I can make out that TACC and GGTT which is there. These are my start and end points. So I will start, let's write down, I will just copy it in a small size and then we will build the graph. So I start, for example, TACC. This is my pair, which is the starting. And when I start, so it gives me TATCCA. And my endpoint I write down here. So my endpoint is this one. GT and this one. TT. Okay. Now see from TACC, I can go where? Do I have some TACC here anywhere? Can you see anyone? Bhavya?
Yes, sir.
So from here, can I go anywhere from TAT or CCA?
I don't think so.
Okay, so can we take the only northern route okay, TAT? So from AT, I can go to TC. Okay, so I can go to here, AT to TC. And from CC, I can go where? I can go to CCCA. So CA is going to AT. Okay, so this we have covered. This part we have covered. TAATC we have covered. CCA we have covered. CAT we have covered. Now from AT where all we can go. So we have to check. So AT we can go to TC. 80, we can go to, this was ATG, if I'm not wrong, this is TG, sorry. Shall I explain on the notes again? This has become slightly long.
Yes, it's much
Huh.
complicated.
Yes. So one part we saw that if we see the single read, single pair, so it can give you two paths by taking the north and by taking the south. And if we solve the same problem, solving the two pairs, so these are the pairs when we have, for example, now making the graph and finding path. So these are the pairs which we have got by using d is equal to 1. Now, the second part is that we put them alphabetically. So we have put them alphabetically, taking the upper wala portion. Now, the same, we find the starting path that with the prefix, which is not the suffix anywhere. So we get, for example, we get the TAGC we got. So from TAGC, when we got, so we now, so TAGC is where? So I will copy from here and I'll explain this example. Because that is slightly long. Okay, is this visible to all of you? Clear?
Yeah.
Okay. So see,
Yes.
here we found that which is the, first of all, the starting point. So starting point, we found that this is the TA which is there. It is not there in any suffix. So we start with TAGC. Now from TAGC, we can go to only AACC. So we cover this full part. So we come here AACC. Now second, now we see come to AACC, which is starting. So AACC starts from here. So we can go from here to AT and CA only. So we go to AT and CA. Now second, now from ATCA, now we check from ATCA, which is the pair. So ATCA is this. So we can go from here to TG and AT only. So we come to TG and AT. Now TG and AT, we have got two pairs, TGC, ATG, TGG, ATG. So what we can do, we can separate them in two parts. One, we go to GC and TG. So we have come here. And second, we come to GG and TG. So we have come here. So till here, we come and we keep on striking whichever part we have covered. So we have covered here till now. Now we see, for example, we have taken this path. So from GCTG we check. So GCTG, do we have GC and TG? So we have got GCC, we can go to CC and TGG. So this is the part. So from here we can go to CCGG. So this we strike. Now we are at CCGG. So CCGG is this. From here we go to CA and GG. So this we have covered. Now CAGA we check. Is there any CAGA is there? So there is a CAT. Yes, this is the one. So CA and GA is there. We go to AT and GA. Now from AT and GA, we can go to ATG and GAT. So this also we have covered. So we go to this ATG and GAT and ATG and GAT, which is there. We come here and ATG and GAT is coming back here. Now we are left with this one, the south part. So we come to GGTG. So GGTG we are here. We can go to GGG and TGT. We come here. And from here, we come to the last, which is there, GGA and GTT. So this is my endpoint. Now, benefit of doing this is what? Now, if we make a path, so the path will go like this. The longest path, it goes here, makes a circle, and comes back here. So there are no two paths. So here we get a unique path. Is that okay?
Yes.
Okay, so this is the benefit. In any PYQ, they have not given this long question, and I don't expect them also to give. In case they will give, it will be a shorter one, and then we can do that. We have seen the methodology how to do that. Is that okay?
Yeah.
Okay. Okay, so with that, okay, so this was the last concept, okay, and it was slightly lengthier, quite exhaustive. Now we come to the PAs and GAs of the week 3. So the question 1 is, from among the options, identify the result of paired composition 3. 3-1. So 3-1, what is the meaning of 3-1? So this, I will just solve it here. This kind of question can come in the PYQ. So here in this 3 is the K. K is equal to 3. And this 1 which is there, D is equal to 1. So how to solve this? That we take TAT, we leave one D1, leave this, and take the second pair, GGG. Okay. Second, we come to ATG, and now we come to GGG. Now we come to TGG, and it will be GGT. This will be GGG, and this will be GTG. Now we come to again GGG, and this will be TGC. Okay, and we can see how many pairs will be there. So 1 GGG. So this we have got. And now just compare, okay, this with your answer, and we can write. Is that okay? This explanation?
Yeah.
Okay. Okay, so we have to check, okay, for example, here they are given, so we can compare and we can get. So I have told you how to do that. In my notes, okay, that time I had not considered this. I had forgotten to see this D is equal to 1. That's why I had solved for everyone. D is equal to 1, 2, 3, 4 also. Second question is this one. Which of the following is so this also we solve, because mainly questions in the PYQs are of the similar nature. So they are asking which of the following is a k-mer composition of the string, this one, given k is equal to 3. So first of all, we can find the number of k-mers straight away. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be 10 minus 3 plus 1 is equal to 8. So anything which is more or less than 8 is straight away we can cut it off. But in this case, 1, 2, 3, 4, 5, 6, 7, 8, all are 8. So all are valid. So if they are valid, now we can make the compositions. And composition, we know how to build it. So TAT, ATG, TGG. And how do we do that? We find all these 8 k-mers and then order them alphabetically. Okay, and then you can compare which are the ones which are matching. Sorry. So it is a simple problem. We can do that.
Yes.
Yeah. Okay. Now this is a question which is of the 4 k-mer, and we have to. That is a subpath of an Eulerian path. Which of the following might be the part of the correct DNA string? Okay, so this we can check. This we will solve. Okay, so they have given this path. So how to build from here and how to find. So the concept is like this, that this is a node and this is a node. So see which are the common here. So see here, C, C, G and A, they are common in this. So what we can do, we can write A, C, C, G, A. We come till here. And this A which is there, it is a extra. So this A will come here. Is that okay? We take this full and we cut the common part.
Okay.
Okay, now here we see again we cut. Okay, now we know that it is having 4 common, so we can strike 4. So now we get G. Strike 4, we get C. Strike 4, we get T. So this will be the answer. Is that okay?
Yeah.
Okay, so it is easy also, and we can do it quickly. Okay. Okay, composition 4. Okay, this is a simple question. This we can do easily. It is a Kmer 4, and just by using the sliding window, we can make that from here. Anybody, any difficulty in doing this? Do you want me to solve this? Anyone?
Yeah.
Huh? Okay, so first, what do we do? First, we find the number of Kmers. So number of Kmers in this case will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 minus 4 plus 1 is equal to 11. Okay, so whichever is not 11, we can cut it off. So we can see 1, 2, 3, 4, 5, 6, 7, 8, 9. So straight away, we don't need to check this. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is a valid one. This is also valid one. This is a valid one. So out of this, now we have to check. So what do we do? Now we start putting alphabetically. So see, how do we do that efficiently? So I know that ATGT and AGCC are the ones which are starting with A.
Yeah.
So the first one has to be AGCG in alphabetically. So this is the only example in which AGCG is there.
Yeah.
So straight away I can cut them and I can write a correct answer.
Yeah.
Okay, so this is how we can do it efficiently without solving the full. We can check this and do this. Okay.
Yes.
Okay, composition 5 ATGT is something where this represents the size of a set. So choose the correct result. So this again, we have to use the formula n minus k plus 1. So n here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 minus 5 is equal to 9. 9 plus 1 is equal to 10. So straight away we can get the answer. Is that okay?
Yeah.
Okay. Okay, so this is one interesting question. This we can solve, and why we are doing that, because somebody had told yesterday that this time they might ask some trickier questions also, because previous PYQs are easy. So we will check this. So the question is, consider the overlap graph representing all the connections between the nodes representing the 3-mer composition of this. So what should be the number of nodes and the edges in the graph? So how do we do that? We know the process of this. So first we build the Kmers for this. So Kmer is TAG. It will give TAAG, AGC, AG, GC, GCT, GC, CT, CTG, CT, TG, TGT, TG, GT, GTA, GT, and TA, TAT, TAAT, ATA, ATA, and TAC. So this will be TAAC. Now, from here only we know that what will be the starting prefix which will be there, which should not be any suffix anywhere in this. So we start from here, check this. TA is there in the TA, AG is there, AG, GC is there anywhere, GC is there, CT is there, CT is there, TG, TG, GT, GT, TA, TA, AT, TA. So this is one like this, that it will be like a circular. So we can start from anywhere. Okay. So then we check about the what it can be the endpoint. So all are matching. So AG is there, GC is there, CT is there, TG is there, GT is there, TA is there, AT is there,
AC is not there.
AC is not there. So only AC we know in this, that AC is the last one. So we can copy here for this miniaturization and to take help from this to build the graph. Okay. So how we build the graph? We write first AC here. Okay. And can we start with TA? Because it is in the starting. So we write here, for example, TA. So from TA, we go to AG. So this we have covered, TAG. Now from AG, I couldn't go to GC. GC. Okay, this I have covered. GC, I can go to CT. CT I can cover here. Now from CT, I can go. Now this TA which was there, TA had three options. So I could go to AT also. And I could go to AC also. Is this okay?
AC is the endpoint.
AC is the endpoint. So this I can. So this I have covered now. TAT, TAC. And I come here till GCT. Now from CT, I can go to TG. Anywhere TG is there. So I have to make a new point, TG. So CTG is covered. TGT, anywhere GT is there? No, GT is not there. So I build GT. So TGT is covered. GT goes to GTA. So it will come where? It will come here. This is okay? Okay. And AT also goes to TA. So this also goes to TA. So now I covered entire thing and I can find the path also.
Yeah.
Okay. So now we had to find the number of nodes and number of edges. The number of nodes, okay, we have found 1, 2, 3, 4, 5, 6, 7, 8. And number of edges? 1,
9.
2, 3, 4, 5, 6, 7, 8, 9. Is this the correct answer in the GA? Has anybody checked here? Nodes is 9, edges are 12. So where have we made the mistake? Any idea? Anybody? This was the same question. TAG, TC, TA, TAC. Just hold on. We'll check it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is. Okay. Can I go from TA to anywhere else also? TA.
TA2 only AT and AC and AG.
TA to AT I have come, TA to AC I have gone, and TA to AG I have come. Okay. And from. So does this question answer looks okay, incorrect to me? GA Bhavya, any input on this?
Yes, I also think means we have followed the same thing.
Unless okay, they're asking something different in the question. Consider the overlap graph representing all the connections between the nodes representing the schema. What should be the number of nodes and edges in this? So this I had done differently that time, but let's do it again.
In the overlap graph, the nodes are the k-merge basically, right?
This is the Euler's representation.
This is the Euler's here. Okay, so overlap here, we are checking only the that. So let's do it that way also. So we have got, for example, so let's start from TAG, for example. TAG. From TAG, where I can go? I can go to AGC only? Or can I go anywhere also? Else also? Just let's see this solution. So TAG, I can go to AGC. And from AGC, let's copy this just to understand this. There should not be any doubt in our mind. Okay, so we have started with TAG. We have gone to AGC, which is this one. From AGC, I can go to GCT. From GCT, I can come to CTG, keeping CTG common. Now here's from CTG, it has got TG. So I can come TG only TGT. But now from TGT, I can go to this GT, GTA. So I can come to GTA only. Now from GTA, I can give either to TAG, or I can come to TAT, or I can come to TAC. So from here, I can come to TAT, I can go to TAG, and also I can go to TAC. So this I have built. Now from TAT, I can go to ATA. So this is the ATA. And from ATA, again, I can go to TAT because it is TA. So again, I can come here. And from TAT, it has made. So I come ATA. And ATA, I can go to TAG also. Also, I can go to TAC. So this is how this graph is made. Is that understood, or shall I explain again, Akya, how we have done this?
One more time.
Okay. So what we'll do, we'll build again, Akya. So from here. So these are our k-mers. So we start with, for example, TAG. So this is my TAG. I start from here. From TAG, I have to go to a k-mer which first two values are AG. So I can go to only AGC. From here, I can go to GC only. So GCT. So I keep on stacking them. So I go to GCT. From here, I can go to CTG. So I go to CTG. From CTG, I can go to TGT only. TGT. Now from TGT, I can go to GTA. So this is GTA. Now here the things become interesting. Now from GTA, I can go to TAG. So here I can go. I also can go to TAC. TAC also I can go. So this GT I have covered. Now, or I can go to TAT also. So there is a TAT also. So let's write down this as TAT, and there is a one TAC also here. Now this TAT, I can go to ATA, and from ATA, I can go to TAC also. I can go to TAT also, and I can go to TAG also. Is that okay? This one?
Yeah.
And this
How are we going from GAT to TAG?
GAT to,
TAG.
where is GAT? GAT is not there.
GTA, sorry.
GTA. So see, I have to go to a k-mer, which this TA value has to match, okay, with the first two alphabets.
Okay, understood.
Okay, so it will match with TAT, it will match with TAC, it will match with TAG. Now, similarly, when I come to TAT, I can go to ATA, nowhere else. And from ATA, again, I can go to TA. So here again, TA is here. I can go to TAG, I can go to TAC. Is that okay?
Yes.
Okay. And so I've done TAT, I've done ATA, and I have come to TAC, and TAC is the endpoint. So this is my graph. So now we can check 1, 2, 3, 4, 5, 6, 7, 8, 9, and edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12. So thanks for reminding who was that again. Just to otherwise we were trying to make the Eulerian graph again.
Yeah, I'm Jaganmohan Rao.
Hi, Jagmohan. Thank you so much.
Yeah.
Yeah. Can we go to the next question, please?
Yeah.
Okay. So now this is also an interesting question. So this again on the same concept, okay, which just now we saw. So this is also an overlap graph. So overlap graph again we will build. So again we follow the same. So this will be on the same concept. So we can select any node, for example, we can select this TAA. So from TAA, I can go to a node which starts with AA and AA. So here we can see there are how many? I can go to AAT. I can go to AAA. I can go to AAA. AAA. So there are two A's. So here are two arrows. So this I've covered AAT, and AAT also there are two. So this also we have covered AAT. So TAA, AT, AAT, AAA, AAT, AAA. So we have covered this. Now we check from AAT we can go to AT. So AT is anywhere. So there are two ATs. So from here I can go to AT. But if I'm not wrong, Jagmohan, in this we have to build we have to write down all these as separate k-mers in this case when we build the overlap graph.
Actually, overlap graph often I confuse, but De Bruijn graph I am very comfortable with overlap.
Okay. So what do I remember that unlike the De Bruijn graph, here we have to make all them as separate. So from TAA, for example, if I select that I'm going only to AAA, so there will be two separate A's. So I go to this AA, for example. And from this AAA, I can go again to AAA. So, or I can go to AAT also. So I can go to AAA, then I can go to AAT. From AAT, I can go to ATA. From ATA, this TA will merge here. It can come here also. And there is another TAA. So there is another TAA here. So we have covered this also, and we have covered ATA also. We have covered AAT1. We have covered ATA only one. So now again TAA which has come. So again I take another AAT. So this AAT we have covered, and from AAT I can cover this ATA. ATA. So this is also covered ATA. And from there, so ATA we have covered two. So one was here and one was, there are three. So there is another third. So from here I can go to TAT. So this ATA is there. TAT I can go, and this also can go to TAA. And this ATA which was there, it could also come to TAT. So this is also covered. And from TAT, I can go to ATA. So there is another ATA. So one graph will be here, one will be here, and third will be this ATA. So this ATA is also covered. And from this ATA, again, I go to this TA. I can come back to this TA. I can go from here to this TA. Okay. And anything else again in this? Can we check what the question is asking? From among the given option, identify the genome that is spelled out by the overlap graph. Consider TAA as the starting graph. So what I followed that when you are building, so we can check one by one.
Actually, just I'm interrupting. What I do is without constructing this graph, just I follow in that options. I will check and whether everything is covered or not. Like TAA, and
Yes.
the easiest way I found out. That is a hack I found out. That's all. Otherwise, it's confusing for me to this overlapping graph.
Yes. So I also did the same, but just to understand the concept, I had made this graph.
Yeah, correct.
And in this graph, now we can check whether all these paths are existing or not.
Yeah.
So we can cut it off. Okay. So this how, for example, I had also done in the same way. Okay, this is an important one, and this is in the PYQ also. So this we can do the de Bruijn graph. Okay, shall we do it?
Yes.
Okay. This has come in all the PYQs. So de Bruijn we have been doing. Okay, so we know how to do this. So ATG we do AT, TG, ATT, ATTT. This we have seen many examples. GAC, GAAC, GAT is GAAT, GGA. This I think we have done the same example which was there in the lecture.
Yeah, you have to count the unique prefixes and suffixes.
Yes. So we can do that. Okay, we have done this 3 times. Huh?
Yeah.
Anyone wants me to do this? Okay, or we all can do this?
No.
Okay. Chalo, then we'll leave this. Okay, so rest all other questions are same, and then we'll see the PYQs also. So shall we consider week 3 done, and we move to week 4 before taking the PYQs?
Yeah.
Yeah. Okay. Thank you. Okay. So week 4 is basically how to find the sequences or the alignment of the sequences. Basically, in the genome, they know that DNA makes the other DNAs. That is one form. So where this process takes place, it is known as origin. So there are 2 questions that how to find that in the origin, that box where this everything is happening, and second, how to find the ori itself in the genome, because genome is very long. So idea behind that is that wherever this box is there must be some messaging. Some messaging must be there. So messaging means that if we can find a sequence or the length of the characters which are occurring more than often, then we can say that it is some kind of signal that here that process will start. So it is a problem of finding the frequent words problem. So if we have got in the string methods, we have done that if we have got a long sequence and if we want to know the maximum or the most frequent string of size 3, so what we do, we follow the window concept. But when we follow the window concept, then the complexity is O to n square k. The second method is that we take the hash values of that. So for if we have got, for example, only ACGT, then the total number of hashes will be 4 to power k. And then we compare it with the hashes. So it gives the complexity of 4 to power k plus nk. But professor had covered he did not explain in detail that this also can be solved in a linear space also, and using the dynamic programming. So that was the first part, that finding the most frequent string, and by finding that most frequent string, we can find that where is that box and where is that ORI. So that is the first part. Second part of the lecture was how to do the local alignment of sequences and the global alignment. And the motivation behind that was that, for example, if we have found a new genome and some sequence is there, so nature which is there, nature is a tinkerer. Nature is not an inventor. For example, in all the humans, we have got 1 billion long genomes, but only 1 million are there, that is 1 in 1,000. There, the differences are there, the alleles are there. So similarly, if we find a new sequence, then we can compare with the already known sequences to know the characteristic of that. So for that, we want to do the alignment of the sequences and how to do that alignment. So that is the second part of the lecture. So this is the alignment game. So in the alignment, we follow that if we follow the scores. And how do we calculate that scores? That if there are matches, we get positive values. Then these are the indels, insertions or the deletions, they are known as indels. We deduct some things for that, and there are mismatches, then we put the penalty for that. And then depending on the best score, then we say that yes, these two sequences are matching. So this is the second method. And professor also covered that this sequence matching which is there, or finding the longest common sequence problem, it can be solved by the dynamic programming. And he drew the parallelism by giving the example of finding the Manhattan's longest Manhattan distance, and Manhattan's distance can be found using the DP only. And the motivation for the DP dynamic programming had also come from the Manhattan distance only. So using this dynamic programming, we can find this maximum common subsequence also. So taking an example from Manhattan, so we, like in a dynamic programming, we make a table and we remember the values which are existing in that table, so that when we revisit, we know that value and we can take that value and use it. That's why the dynamic programming is efficient. And how do we do that in the alignment of the subsequence? That when we are aligning two subsequences, so if there is a match, so we give a value of 1 to that. And if there is an indel or unmatched, then it is 0 in the starting. Further, we will see that we can give penalties also for different combinations. So this was one example how we find this. And what I'm expecting in this time question paper, like they have mentioned that they will make it slightly trickier, because in the earlier PYQs, they have not asked a question like this in any PYQ. So this time they might ask a question from this kind also. So they will give us a graph and to find how to find the path or how to find the alignment. So I will advise everyone just go through these notes also or through the lecture also. You'll get an intuition how to solve this. It is very easy. Okay. The pseudo code which is there, it is that I will cover here. So this is the dynamic programming pseudo code. The Sij is the length of a longest path, and we have to start from the starting point and we have to end the last point. So Sij is the length of the longest path from 0, 0 to ij here. So Sij will be the max from Si minus 1. Si minus 1 means here, this row which is there from the previous row, plus weight of the edge which is on the top. So if I'm here at this node, its value will be there max of, I'll just zoom this out and just to understand. So can you see my cursor, all of you?
Yes, yes.
Okay. So the value here will be the maximum of either the value which is here or value which is here, or it will be the value which is here plus the edge length of this. If it is a match, for example, I just take an example. I'll just copy it on my. here. Okay, I'll just explain here. For example, in this case, okay, we built, for example, here. So AA, it is matching. So here we will get a value 1, or we write this as 1. Okay, 80, they don't match. So this is 0. 80, they don't match. So this is 0. So what do we do? First, we fill the first column. So this is 0, 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 this is 0. Now this AA is matching. So this value will be there. This value, x, for example, x will be max of Si minus 1, I minus 1, which is this value. Then Sj minus 1, which is this value. And max of this value Si minus 1 and j minus 1 plus weight of ij. So in this case, this weight ij is 1. So it becomes max of, this is 0, this is 0, and this is 1. So here it becomes 1. So this value will become 1. Now, when you apply the same formula, now you will get this one, this one, this one, this is 1. This will also become 1 because this is 1, max of 1, 0, and 1 is 1. Here it is 1, and here it is 1. Is it okay with all of you? This part?
Yeah.
Okay. Now see, when I come here, this is 0. So starting, we fill the top and these values. So these are 0. Now when I come here, this value will be the max of this value, and this value. So again, this becomes 1. This will become max of 1, 1, and this is weight is 1. So this will become 2. So this will become 2. And this 2 will perlocate downwards. Now, is that okay? Now here, what will be the value? It will be 1. Max of this, and this plus weight. So this is 1. Here it will be 2. This will be 2. This will be 2. This is 2. This is 2. This is 2. This is 2. Okay. So this is now 1. This will become 2. Now this will become 3 because here 1 will be added. And this 3 will come downward. Okay. Here it will be 1. Here it will be 2. Because this will also become 2. This is 2. Max will be 2. This will become 3. This will become 4. 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 Here it will be 1, 2, 3, 4, 4, 4, 4, 4. This is 1, 2, 3, 4, 4, 4, 4, 4. Is that okay?
Yes.
Now, how to find the path here? So, see, this is the starting and this is the end. So now we know the length of the path is 4. So we start from here and we have to follow from where it has come. So it has come, it can come from anywhere from here to here. So in this case, multiple paths are possible.
Yes.
Okay, either I can go from here 4, 3. Now I will go to this 3, 3, 3, 3, and this has come 2, and from here 2 has come from here, and then I can go here. Or I can go 4, 4, 4, 4 here, and I can go like this. Okay, so in this case, multiple paths are possible. Okay, so we'll solve another question like this, just to get the concept clear. Okay. So this was how we find the path and how to fill this and how to use the dynamic programming. So just go through this pseudocode examples. So pseudocode, if you don't remember also, just remember that this value which is there, it is the maximum of this, which is j minus 1, this is I minus 1, and this is S I minus 1 J minus 1 plus weight of this from this to this. So this is the value. And when you do backtrack, so backtrack, either you will do top or you will do west or you will do here. So you will go from where that value is coming. For example, in this case, this 4 has come from everywhere. But for example, if I want to do backtracking from here, so this 4, it has come either, not forgotten, either it has come from here or it has come from here. So backtracking can take place to both sides. So it can go here also, here also. And from here, we can check what are the values. So if it has come from here, then I follow this path. And then I see from where this value has come. This value has come from here, and this value has come from here. So this is how I build the path. Okay. Okay, with this, can we go to the PYQs, please?
Yes.
Yeah. Okay.
Yes.
Yeah.
Okay. Okay. PYQs are much easier than the GAs and the PAs. So that's why I said this time they might ask a little bit of trickier questions just to make it slightly difficult. Okay, so we had covered till here yesterday. So the first question is on the pseudocode. So the pseudocode is that given a multi-set of k-mers, Sk, the pseudocode of the algorithm to construct the de Bruijn graph G is given below. Fill in the 4 blanks. Multi-set Sk is equal to collection of input k-mers. So remember the de Bruijn steps, how we had built. And if you remember the steps, then you will be able to easily solve this question. So I'll just write it down here. So in the de Bruijn path, what we were doing, that for example, we had small example I'll take. We had ATG, ATC, and CTC, for example. We had this. So this is your Sk. So Sk is equal to this collection of input k-mers. And set Sk minus 1 is equal to 5. Sk minus 1 is equal to nil. So there is nothing. For every I in Sk, for every I, so we take, for example, ATG, add I to 1 to k minus 1, that is AT, and I to k to set Sk minus 1. So what we are doing in this step, we are making this Sk minus 1. So this will become AT, TG, AT, TC, CT, and TC. So this we have done in this step. Second step, they are saying, for every I in dash, add the node to G. So from here, now, graph which is there, we add from Sk minus 1. So here it has to come, Sk minus 1 has to come here. So then the graph will become, so this will becomes the graph, AT, TG, AT, TC. So this is my graph, CT and TC. And now for every I belonging to Sk, so now I take ATG, add the edge from this to this. So from which to which I will add? So I will add from, I take the clue from here, I'll be adding from I to 1 to k minus 1 to I 2 to k. So this how I can get the intuition how to find the solution. Is that okay with everyone?
Yes.
So this
Yes,
is your
sir.
Sk minus 1 and add the node to G. So I will add I to this. And for every this, then I will add I 1 to k minus 1 to I 2 k to G. So this is how I can do this question. Okay. Okay, second question is the following reads are found from a genome sequence. So this is a de Bruijn graph. We have done enough questions on this. So the steps, they remain the same. So what do we do? First, we convert these reads into the pairs. So here we have got the pairs. Then we find the start point. So in this example, in this question, there are two start points. If we see TT, so there is one TT which is not there in any suffix, and then there is one AA which is not there in any suffix. So this straight away gives me an idea that I cannot find any path which will, visit all these k-mers. Then I find the endpoint. So the questions are there. Question is there: how many nodes are there in the corresponding de Bruijn graph? So endpoint I have found TC, and using the same philosophy which we have been using till now, and then I build the graph. So there are two endpoints in this, TT and TC here, and starting point. Okay, sorry, two starting points, AAA and TT. We started, and there is one endpoint. So if we do that, we find, okay, the total nodes are 10. Anybody wants me to do this question again, or we can do that? We can
No.
hack it. Yeah. Okay.
No, sir, all clear.
And the second question was, which among the following statements is true? So first is the underlying genome can be constructed. Second is also can be constructed. Third also can be constructed. The fourth is only there, the underlying genome cannot be constructed. Why? Because there are two endpoints, two start points. So that's why the last option is correct. Is that okay?
Yes.
Okay. Second question is, consider two input DNA sequences. These are the ones. These are the matrices which are used to calculate the score. So what is the alignment score for the global alignment between following two strings? So in this question, there is only one catch. Please remember in your during the quiz that this sequence which is there, this is the N sequence. So N sequence comes here, and this is the M sequence. Okay. So when you are doing the comparison, so this will become G and indel. Have you understood? Have you got my point? This one?
Yes.
Okay. So don't think that that we have to take indel G. So if we take indel G, then it is -3. So we have to take G indel. So G indel is -2. Okay, that is the only catch. Otherwise, it is simple mathematics. Is that okay, Bhavya?
Yes, sir, got it.
Okay, this is N and this is M. So this is row and this is column. Only. Okay. Then consider the global alignment between V and W. So please check the question carefully. Global alignment means that all have to match. Okay. So in this case, we had this total. So total all have to match. So this TTAC and TTAC is not a global alignment. So we have to straight away discard this. And then using this formula, we can check all of them and we can find the score. Simple mathematics, nothing else. Which among the following statements is correct? Global alignment involves aligning the entire sequences, while local alignment involves aligning smaller parts substrings of the sequence. It is correct. Alignment problem can be solved using a greedy algorithm approach. It cannot be solved. It can be solved only by using dynamic programming. To compute the global alignment between two sequences, free ride, that is zero weight edges, are added from the source 0, 0 to every node and from every node to sync. No. So zero ride, if you remember the lecture, zero ride, what we do, we find some path and from there we get a zero ride. So this is the local alignment maximum. And then again, we find the path. So this is the zero ride alignment in between. The last part, the alignment problem can be solved in linear space. This professor has covered that this can be done in linear space. So this I have written down the explanations also. Then is a simple question mathematics. Global alignment between this, and scores are match +1, mismatch -1, open gap -40, extend gap -1. So just we have to use. There is a efficient way also. So what you can do, you can check the number of gaps, because here gap is minus 40. So here minus 40, minus 40, minus 40. So answer will be somewhere close to minus 120. Here only two gaps are there. So answer will be somewhere close to minus 80. Here again three gaps are there. So here it is minus 120. Three gaps minus 120. So this is your correct answer. So without doing calculation also, you can solve this. Identify the set representing composition. K-mer is 3. From here, we have done this, so we can do it easily. Just make the K-mers and then arrange them alphabetically. Then consider the overlap graph representing all the connections between the 3 K-mers. So Jagmohan, I had not done this using this earlier one. So we can solve this using your now the overlap graph. Can we do this? All of us, we are ready?
Yeah.
Okay, so what we do, we start with ATT. ATT. From ATT, I can go to TTC and TTC twice. So TTC and TTC, I can go twice here. From TTC, I can go to TCC only. So this TTC and this TTC, both TTC will lead to TCC. So ATT is cut, TCC is cut, TTC, TTC is cut. Now from CC, I can go to CCT only. From CCT, CT, I can go to CTA and CTT. So CTA and CTT, both I can go. And so CCT I've done, CTA. So CT I've covered, CTT I've done. Now CTT, I can go anywhere from TT. TT. I can go to this. I can go to this.
Yes.
And TA, I can go anywhere. No, I cannot go. So I am left with GC. Can I do this GC anywhere? So I'm left with TGC also.
TGC and GCT.
So where they will come? Okay, TCC is there, CCT. So we have not followed that principle just to check which is the starting one and which is the ending one. So can we do that first? So let's do AT. Is AT is anywhere? AT is not there. So definitely your starting is ATT. ATT, I can go to TTC and TTC. TTC, TTC. From TTC, I can go TC, TC, TC. I can go to TC. And from TC, I can go to CCT. CCT. From here, CTA.
Actually, to solve the question from exam point of view, there is much easier hack for this actually.
Wo that finding the length?
No. If you find the options,
Yeah.
they are given like a triple T, then a CAT as the K-mers in the sequence.
Yes.
So CAT are not available as a K-mer.
Okay.
Triple T is also not available as a K-mer.
Yes, like this. From here we can check.
Yeah, from the options you can find out which are the wrong options. So only
Okay.
one option is left out,
Okay.
which is not covering in fact all the K-mers, but partially it is covering.
Okay. So what I did today, that I followed the de Bruijn path, and from de Bruijn path I found
Yeah,
the
from there
path.
also we can do, yeah.
Okay. So, but
Yeah, sometimes we can apply de Bruijn graph and find the answer, and the same answer will be applicable for the this thing also, overlapping graph also.
Yes. So this is much more efficient. So here I did in your way.
Yeah.
So I found a k-mer which is not there.
Yeah, I can see in the options, like a triple T. Triple T, there is no k-mer, such k-mer like triple T.
Yes.
And CAT also. CAT is also not available.
Yes. So here also TTTC, here also they have given
Yeah.
again. So it is not there.
Yeah.
Okay. So all of us, we got this, okay, how to do it. So we
Sir,
can.
can you just explain this hack with the question and the options so
Okay.
I can get an idea?
Okay, I'll
Just if you allow me, I have opened that question. If I present
No,
that.
it is there, okay. My
Yeah,
screen is visible, no?
Yeah, okay.
Okay. Yeah, just hold on. So see, these are the 4 options.
Yes.
These are the 4 options. Okay. So see what we do. This one, if it has been made, so this will be CCT and CTT and TTC, TCA,
Then CAT,
CAT,
ATT.
and ATT. It will form from here only. So here you see CCT is there. Okay. CTT is there. It is there. TTC is there. It is there. TCA is there. This is not there. So straight away we can discard this. Okay. And see, CAT is also not there. Okay. So both are not there. We can discard straight away. Similarly, we check this ATT. This will be TTC. This will be TCC. No, not TCC. ATT, TCC. And from TCC, CCT, then CTT to TTC. So here we check ATT is there, TTC is there, TCC is there, CCT is there, CTT is there, TTC is there. So this is possible.
Yes.
Okay, now we check this ATT, TTT. So straight away we can check this TTT is not there anywhere. So this is not possible. Okay, similarly you see here TTT is there. So this is also not possible. Is that okay?
Yes.
Yeah, thank you. Now we go to next question. DNA sequence, mathematics, simple. This question has been repeated so many number of times. So we have to find the score. Match is +1, rest all is 0. So we can just straight away calculate the number of matches only. Okay. Then here they have asked global alignment in scores. So in the global alignment, this will not be this global alignment. Rest all we find the score and using this formula. In the next question, they have asked the highest score in local alignment. So when they are asking local alignment, we have to consider this. And when you'll consider this, you'll find the score of this is the best score. Okay, so these were the only PYQs in this. So what today I saw, the ratio or the proportion of week 1 and week 2 is slightly higher than the week 3 and week 4. And the questions from week 3 and week 4, they have asked very, very simple and easy questions. So this time they might ask some difficult questions. So especially the graph, the Manhattan distance one, and how to find the path here. So that kind of question can come in a graphical form. So we all should be ready for that. So with that,
why there are only 2 PYQs for ATB? Means it's a new course or what happened actually?
There are only 2 PYQs. I think it was not available in all the terms.
Yeah, that's why I wondered. I wanted more to practice, but I did not get.
Yeah. So, and what my understanding is that here the concept are clear, like in the ATB.